Hi, so this is a video editorial for the LeetCode weekly contest 502. This time I'll say the problems were quite good. Like especially Q4, I really like that problem, and like my performance was decent. I spent some, even though like I took some time to get the idea for Q4. I did spend some more time debugging some silly mistakes, but outside of that, I guess my overall performance was all right. So in this like editorial thing, I'll be going through my solutions for how I implemented the problems in the contest in the order one to problem four. And then after I've discussed my solutions, I'll attach a live solve section which will show how I approach the problems in the live contest itself. All right, so Q1 was fairly straightforward. We are given a string of digits where length is less than 100 and s is only digits, so 0 to 9. And we had to return true if the absolute difference between any pair of adjacent digits was at most 2. Else we return false. So like this was fairly straightforward. All we had to do was just run this loop and check, like if x is greater than 2, that means absolute difference is greater than 2, we return false, else we return true. So Q1 was that. Q2 is basically we are given a range L to R and K, and we are given y is this equation y is greater than is equal to x power k, right? So given a range L to R, we have to find the number of y's such that they are perfect kth powers, right? So if k was 2, we have to find the number of squares in this range. If k was 3, we have to find the number of cubes in this range, and so on. And of course, we have this L less than equal to R, and this range is from 0 to 10 power 9, and k is up to 30. One second. All right, so yeah, my implementation for this was basically this idea. One second. We are given a range L to R, right? If k equal to 1, that means we have this equation y is equal to x power 1. So y is equal to x only, right? So in this range, in this case, the entire range would be the answer. So we will have, yeah, we would have this r minus L plus 1, right? Because the entire range is the answer. So this is for k equal to 1, because like, and like for the other case, my idea was, since we are now iterating on squares, like in the worst case, now if k is greater than equal to 2, the worst case for us would be when k is equal to 2, right? And our r is equal to 10 power 9. In this case, if we iterate on all the squares, then our complexity would be root r, right? So which can pass for 10 power 9. So basically, like for this case, the answer would be just do this, the O of 1 solution for k is equal to 1. Else what I did was I iterated like this. I iterated on all the power k's. So basically, I'm x is my base. I'm getting the power y. So y is equal to x power k, right? And here you could use that, the inbuilt power function, but that can give some floating point error. So just to be safe, I just did this, which in the worst case is O of k itself. If my y is greater than r, that means I'm out of the range, I break. Else if it is inside the range, only then I increment the answer. So the overall complexity for this solution is this. The main thing here was splitting. Like in case of the main thing here was like in case of k be equal to 1. If k equal to 1, the answer is O of 1. Else it is root, basically. Else it is O of r power 1 by k into k. Because I'm taking O of k to calculate the power, right? So yeah, this was my solution for this. Q3 was an interesting problem as well. Basically, we are given this matrix, and into a matrix where let a value at x be this, right? X, whatever. Now we have to find the number of local maximums in this matrix, and a value is at a value at a row at some I comma j is a local maximum if it follows this rule. Basically, let 2 be the I comma j, right? So all of the values inside, assume it's grid, like where the difference between the row and column is less than equal to this 2, and ignore the corners where both the distances, what do we say, both the row and column distance is equal to 2. So we have this plus sign, right? So for every value we'll have this plus sign, and in that case, if this value is the local maximum, and local maximum here means basically no other value in this plus is greater than that value. In that case, it is a local maximum, so we have to count the number of local maximums in this matrix. Now, one idea is obviously you could brute force this search for every value, but since n is less than equal to 200 and the values itself are less than equal to 200, that won't work. So my idea here was, since one second, since less than equal n power 4 won't work for n less than equal to 200, n cube can still work, right? So basically this was my idea. What I'll do is let I be at some I comma j. For every row which is inside this, I know if it's the top or bottom row, then the query range is still, else the query range is basically j minus x and j plus x minus 1, right? We have this range. J minus x plus 1 and j plus x minus 1. We have this range. We have j minus x and j plus x. Yeah, we have this range j minus x and j plus x. So inside this range, if the maximum is greater than this, that means that this is not the local maximum. So my implementation was, obviously this is not the intended solution, and I'll be sure to check the actual solution for this. But what I did was I made n sparse tables, like one for every row. And for this, I went to the topmost row, which is I minus x. And in the topmost row, I queried this range and got the max. And then from the bottom, and then for these rows, I queried this range and got the max. And then for the last row, I queried this range and got the max. And I maximized all of those. And if that was greater than this, then I'm not adding to the answer, else I'm adding to the answer. And obviously, if x is 0, we do nothing. So this was my solution. I think our 2D sparse table would work here as well. Basically, we would query this range and we would query this range and get the max, and since since the maximum is an idempotent function, it wouldn't matter even if the region is overlapping. That is the intuition behind sparse table as well. So if we use a sparse table, then this would be, if we use a 2D sparse table, then this would be solvable for n less than equal to 1000 as well. So yeah, be sure to check out 2D sparse table solution as well. I myself at this point don't know 2D sparse table, but I'll check that idea. So this was Q3. And Q4 was a nice problem. Basically, given an array nums, we have to find the smallest subarray which is distinct, like which occurs only once. So here, like 3 occurs like more than once, right? We have 3 here, 3 here, 3 here. If we check the array 3, it also occurs twice. We have 3, and 3. But the actual subarray 3 only occurs once, right? So this is the problem statement here. Like the answer is 1 because the subarray 1 only occurs once. All of the other subarrays, since we want the smallest, this would do for us. And here the answer is 2 because like 1 does not occur once, it occurs more than once, it occurs thrice. 2 occurs twice, but 1 or 2 occurs only once, right? So the smallest length is 2, where this is distinct. So this was the problem statement. And the length n is less than equal to 10 power 5, and the values are less than equal to 10 power 5 as well. So yeah, this was the problem statement. My initial idea was maybe some sort of like string automaton would work here, like ahogorasic or like suffix array, but like I am not that good at ahogorasic and I don't know suffix array at all. But so I was trying to look for some other solutions. And my first observation was this length is monotonic. Like I think I wrote here as well. Yeah, if length 2 is identical, then length 1 is also identical, because assume like, 1 second. My intuition for this one, assume we have this is the array, right? And I'll mark the identical region here. Assume we have this subarray which is identical to this subarray. If this is identical, then its subarrays itself, like if its constituent subarray here would also be identical, right? So assume the red length is k and the blue length is k dash. If k we find if k like, and this is for all of the cases, like there is no such subarray of length k which is distinct. If we have this condition, like if no such subarray of length k is distinct, that means no such subarray of length k dash would also be distinct, right? Since all of the subarrays of length k dash and k dash and k dash is less than k, right? Since it's a constituent subarray, no such subarray of length k dash would also be distinct. So for that basically means the answer is monotonic. If k is not an answer, then k minus 1 is also not an answer. And if k is an answer, then k plus 1 is also an answer. We have this. We have the monotonic range. Basically, it's like this. Not an answer, not an answer, not an answer, not an answer. And then we'll start having answers. And then these are the good values. That means we can binary search on the smallest such good value, right? And like, let's say we are now, the problem statement is a bit easier for us. Let's say working on a checker function. Let's say we are working with some length k. And we have this array. Yeah, we are working with this array. We have length k. Now, my idea is here basically. Let's say we are checking for this. Obviously, we can't run this loop again and again, right? If the length k, length k subarray with the exact same values exists elsewhere. So my idea here was maybe we can hash this region. 1 second. If we can somehow hash this region, and if this hash of size k only occurs once, that means this subarray is distinct, right? And obviously, if we are hashing, we'll have hash collisions. So we'll try using a double hash here, which was my implementation. Now I'll explain the remaining during my implementation. So here, like obviously the smallest answer is 1 and the largest answer is n, right? Since the n is guaranteed to be the answer, since the entire array will only occur once. So I have this substring hash. This is basically a template I made a while back, which basically, like, the actual implementation is not important, but this function is important. For some, this, what do we call this? This get hash function returns the substring hash of the range L to R. And basically it uses the inverses and all to find the hash of just that section. This is not required. You could calculate a running hash, but since I had this template, why not use it, right? So so now when I'm checking, and obviously we have two hashes, A1 and A2, which constitutes with A1 is mod 1, which is 10 power 9 plus 7, and radix 1 is 10. This is basically 1e5 plus 3. I just found the smallest prime, the prime numbers, and this is 10 power 5, right? So since the values are less than equal to 10 power 5, we want the radix to be at least 10 power 5. So which is why I took these two as the radices, I guess, and these two as the mod values. And I put them in my this template. Like, I guess you can pause the video and look at this. I had to make some changes here, but regardless, all right, we have this, right? Now in our actual function, what I'm doing is, this is the k for which I am binary searching. Now for some index, this obviously the first will be k minus 1 only. We have this range, right? L to R. Let I be the R range. First we get the hash 1 from the A1 substring hash, then we get the hash 2 for the A2 substring hash, and we just add it to the frequency map. Now I'm doing this get hash. The thing is, since we have two hashes, right, of both, let's say like 9 digits, actually 10, both will be 10 digits. Since we have this, our mod is 9 plus, let's say 10, right? Both are less than equal to this. So what am I saying? Yeah, so basically our both of our you'll have this, right? 10 power 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, we'll have this, right? Now, since we have two hashes, either I could have used a map of pairs, like map a pair long long. But what I did instead was this was like hashing is already a runtime intensive task, right? We are doing this operation, we are like doing multiple operations here. So for that, instead of doing that in my hash, instead of making a map of pairs, which you can try as well, I basically took two of my hashes. One second. Yeah. So this is my H2, this is my H1. I basically shifted my H1 by this amount and then I just added them. So basically we have the left, this however many digits here are assigned to H1 and the remaining are assigned to H2. The map approach would also work here. I'll show you map, but it's obviously going to be reverse runtime. There's some issue. 1 second. This would be in first one. Three, one, two. Yeah, all right. This is going to be like, this should be verse runtime. There's some. All right, this hasn't loaded yet. Yeah, this is 1200 seconds and the previous one was 900 milliseconds. 1200 milliseconds and the previous one was 900 milliseconds. Right? So this was my idea. Instead of hashing as a pair, I just took the left hash and shifted it a bit. So basically, if my left hash was, let's say, like some whatever value, it gets shifted, and my right hash is in this right half, and my left hash is in this left half. So yeah, basically this was my implementation. This get hash function here is basically doing this, shifting the right hash on the left hash by this amount, and then we are just adding this thing. And now at the end, if any hash occurs one time, this should be equal to 1, but doesn't matter. If any hash occurs one time, that means it was unique, right? So in that case, we return true, else we return false. And I guess there would be some suffix automaton solution for this, which I'll have to look. But yeah, outside of that, this was my solution for Q4. And after this, let me know if you have any doubt on something. And you can watch how I approach these problems in the live contest. All right, bye.
सॉरी टू इंटरप्ट योर म्यूजिक, पर क्या आप इंस्पेक्टर विक्रांत सिन्हा के बारे में जानते हैं? अरे वही इनकाउंटर स्पेशलिस्ट जिसके खिलाफ वो एमएलए अशोक पावरकर षड्यंत्र रच रहा है। वो फंस चुका है सुल्तानपुर के माफिया के दलदल के बीच में। नहीं जानते आप? कोई बात नहीं, आज ही जान जाइए। सर्च करिए इंस्पेक्टर विक्रांत सिन्हा ओनली ऑन स्पॉटिफाई और जुड़ जाइए विक्रांत सिन्हा की कहानी के साथ।
हेलो दोस्तों, मैं हूँ डोरेमोन और आई शुड से द वॉइस ऑफ डोरेमोन। हे गाइस, इट्स मी सोनल और मैं आपके लिए लेकर आ गई हूँ शो। इस शो में मैं आपको मिलवाऊंगी कुछ ऐसे वॉइस आर्टिस्ट से जिन्होंने आपके फेवरेट कार्टून कैरेक्टर्स को आवाज देकर आपका बचपन बनाया है यार।
डोरेमोन डोरेमोन मुझे गैजेट दो ना। पिकाचू थंडरबोल्ट इस्तेमाल करो।
तो जल्दी से स्पॉटिफाई पे द मोटर माउथ शो सर्च करो और फॉलो करो और सारे एपिसोड सुन लो। अगला एपिसोड बहुत इंटरेस्टिंग होने वाला है।
Who said you can't time travel यार? मैं तो अभी कॉलेज का चक्कर लगा के आया. वही कैंटीन की मस्ती, रूम 12 की सीक्रेट पार्टीज, सब याद आ गया बॉस. Thanks to my time machine. I mean Spotify repeat rewind playlist. वही पुराने favorites और full flashback. Wish it took me back to my first crush. Never mind.
Rediscover your old favorites with Spotify's Repeat Rewind playlist. Explore now.
Planning my engagement party was a pain. From picking my dress to his dog's dress. Ugh, too much to do. And then there was music too. But thank God for Spotify's song radio. I just picked one song and फिर उसने पूरी vibe set कर दी. I didn't even mind dancing with the aunties then.
You pick the song, we'll set the vibe. Just tap on the three dots, select song radio, and let Spotify do the rest.
Goodbye is okay. Now that the men have zoned out, we have only 30 seconds to get through to you.
I'm Sakshi Shabdasani.
And I'm Nana Bhan.
And Moment of Silence is a yapathon for all the strong, independent women who want to laugh at their problems.
20 seconds left. Okay, we talk about love, exes, weddings, therapy.
And why men will literally do anything except go to therapy.
10 seconds. Just listen to the podcast.
Just go search for Moment of Silence on Spotify and stream now.
Ah!
क्या कहा? वो वापस आ रहा है?
आने में जरा देर कर दी। स्वागत नहीं करोगे हमारा?
काफी इंतजार करा दिया आपने।
वक्त से पहले आना मेरी फितरत में नहीं। हाँ मैं बोस, भास्कर बोस।
M&M Talkies presents Bhaskar Bose, based on the Spotify original. He is here.
Good.